So welcome to another session of Everyday Mathematics. Today we continue on this journey on calculus, and we look at the second session on the topic of sets. And we'll begin first of all with the notion of what product sets are and what index notation looks like as regards sets. So one quick thing I would like to say is that if you have a function that transforms set A to S, all the functions that do that transformation can be designated as S to the power A. Such that if you have this R, which is just a set notation for all real numbers, to the power R, this is a set of real valued functions on one real variable. So that's how you denote it. And so Z to the power positive or plus is simply a set of all positive integers. So S to the power Z to the power plus is a set of all infinite sequences in S. Now if you have n bar being equal to a set of 1 all the way to n, then S to the power n bar is a set of all finite sequences or sequences of length n in S. If you have a function of single ordered pairs, we talked about ordered pairs, x and y, that could be viewed as a function that is a subset of the Cartesian three-dimensional space, that is R to the power 3. If you also look at a set of indices I, the index set is designated as x subscript I, where I is an element or a member of the set I. Or you could just denote it as a set of x to the base I, and here we have a subscript of I being a member of small I being a member of capital I. Into the topic of product, a Cartesian product of A and B and C is a set of all ordered triplets, x1, x2, x3, and we know x1 B is an element of A, x2 is an element of B, and x3 is element of C. So the Cartesian product of A, B, and C is just a set of all ordered triplets or triples of x1, x2, and x3. So just as an example, if you have set A being 1 and 2, 1 and 2, and set B being 3, 4, 5, then the Cartesian product of A and B is a set of 1 and 3, 1 and 4, 1 and 5, 2 and 3, 2 and 4, 2 and 5. So it's a set of ordered pairs with each element in the pair coming from the sets you're trying to obtain the Cartesian products A and B. More generally, if you have A, Cartesian product of A1, A2, A3, A4, all the way up to AN, or using this product symbol, so that simply is a set of ordered n tuples x being equal to x1 all the way up to xn, such that xi is a member of AI. In other words, x1 is a member of A1, x2 is a member of A2, and xn is a member of AN. So that covers quickly the issue of product sets, and then on the issue of composition, if f is a function that transforms set A to set B, and then set G, if function G is what transforms set B to set C, then the composition of function G and function F, GF, is a map that transforms set A to C. The definition therefore is G and F, we have this product, this dot in the middle of X is the same as G with Fx inside the bracket for all x's in the set A. There is a lemma to take into consideration here. The composition satisfies the associative law, meaning that if you have F in association bracket G associated to H, that's the same as the bracket being moved to cover F and G. So to continue, a quick reminder that if there is a mapping F that transforms A to B and has both the right inverse H and the left inverse G, then they must necessarily be equal. And the theorem that tells us that mapping F of a set A into B has an inverse if and only if it is bijective. Bijective, we mean that it's both injective and surjective. Injective meaning that there is a forward one-to-one correspondence between input and output. Surjective in the sense that for every output there is a corresponding input. Now in this case, if this is what this function is, if it's a bijective, its inverse is its relational inverse that transforms the output back to the input, negative f to the power negative 1. In the concept of duality, if we have a function f that transforms A and B, it has two variables into a set C, then if we fix x, if x is held, the function fx is a function of one variable y at that particular instant of x. That is, for each x there is a function hx that transforms every item in B to a set C, defined by hxy equals to fxy. And thus, there is this transformation that transforms every item x or in A into hx, and that mapping phi is a mapping that maps items from A into a set of functions, as we said previously, that transform B to C, and that is C to the power B. This mapping phi is interesting. Similarly, for every item y in B, or for the elements of y in B, would yield a function gy that are members of a set of functions that transform A to C, where gyx is fxy, and therefore a transformation of y to gy is a mapping theta from B to a set of functions that transform a set A to C. Okay. So we've told ourselves that this transformation y to gy is a mapping theta from a set B to a set of functions that transform set A to set C. Suppose we have a mapping phi that maps set A to a collection of functions that transform set B to C, and for each member of the set A, that is x. For each x, we designate the corresponding value phi in index notation as hx. So hx is a function from B to C, and we define that capital F is this function that transforms both set A and B to set C. And we do that by now denoting a focus on item X. These are X's, members or elements in C, as HXY. Now we do have these two mappings. We have phi and we have theta. In the concept of duality, in equivalence, we can say that the mappings phi that transform A to a set of functions that transform B to C, and a transformation F, capital F, that transforms sets A and B to C, and theta that transforms set A to a set of functions that transform items in set A to C, these mappings are equivalent. Mappings phi, theta will be said to be dual to each other. In other words, phi takes A to C, B, C to the power B, and theta takes B to C the power A. So this is a concept of duality. Let's go quickly through a couple of Boolean operators. If S be a fixed domain, and we have this sign here to denote a family of subsets of S, the union of this, they call it fractal L, the union of these sets, or the union of all sets in this, is a set of L elements belonging to at least one set in this new family of sets. Very interesting. So we designate the union of all sets in fractal I as u to the power fractal I, or we could say, okay, this symbol for union, subscript A, being members of this set, fractal I family of sets of A, and thus we have union, the power fractal I, being equal to all x's such that there exists an A that are elements to the fractal I in which x is a member of family A, or of a set A. Equally, we could say y is a member of this A raised to the factorial I, and this is equivalent to there exists an A that's a member of this family of sets where y is a member of A. If, for example, this fractal I is a member, it consists of two sets A and B, we designate the union A union B, a notation that displays the listed names. Equivalently, we could say that if X is a member of the union of A and B, that's equivalent to saying that X is a member of A or X is a member of B. If, for example, the fractal I is equivalent to A subscript I such that I is equals to 1 all the way to n, we generally write that the union is A union A2, A1 union A2, A union A3 all the way to A union n. Or we could just say that the union from I equals to 1 to n of AI for the symbolism union to the power, or union raised to fractal I. The intersection of the index family AI is designated as this symbol of intersection, replacing for the union in this instance, and this also is a set of all points that lie in every I, so it's the region of intersection. How we could express this, we could say X is a member of the intersection of I, being a member of I for all A subscript I. This is equivalent to saying that for all I, such that I is a subset of set capital I, X is a member of A subscript I. For an index family of sets, fractal I, we use the formation intersection to the power fractal I, or intersection subscript A being a member of this sets, family of sets, fractal I of A. And if, for example, this fractal I is a composition of two sets A and B, then n raised to the power fractal I, or n fractal I, equals to A intersection B. So the concept of complements, if the complement of a set, for example, A, can be denoted as A apostrophe of a subset S is a set of elements X members of S not in A. In other words, how we would represent A complement is equals to X being members of S but not members of A. And there's another law, the De Morgan law, or the law of De Morgan, states that the complement of an intersection is a union of the complements. The complement of the intersection is a union of the complements. And how we would view it is that if you have two sets A and B, and then you obtain the complement, or you obtain the elements that are outside that area of intersection, it means you are looking at the union of areas outside the two sets, because that's where there is an intersection of things that don't exist in their area of intersection. Or if we express it in this format, we say X being a member of the intersection of items in sets AI for all i's. The complement of that is the same as X is a member of the union of the complement of all items, of all sets in the region. If BI is equal to the complement of AI, then if we use the same rule, the De Morgan law, the law of De Morgan, then we see that the union of BI, all that complement is the same as the intersection of the complement of the independent sets. And this is how you'd express it. What we're trying to say here is that if you have A union B complement two sets A and B, and the union of that, taking the complement, that's the same as complement of A intersection complement of B. And the quickest way you could prove that is if you have this Venn diagram of A and B. The intersection of, this is A and this is B, the intersection of the complement of A and the intersection and B complement is everything outside here, outside these two sets. This is where there is an intersection of that, of the complement of A and B. But then if you look at A union B, is this region surrounded by the boundaries of these two sets. Complement of that is everything outside. And so this proves this first theorem. And you could, go ahead and test the same thing with this second expression. Also, another thing we'd like to quickly remind ourselves, if you have the intersection of A and the union of B and C, that's the same as the intersection of the region between the intersection of A and B union the intersection of A and C. Similarly, if we have the union of A and the intersection of B and C, that's the same as the intersection of the union of A and B and the union of A and C. And this is just another representation of what we see here. Another concept we'd like to say is that the family of fractal I is a family of set fractal I is disjoint if the distinct sets in that family have no elements in common. And this is just a fancy way of saying that for all x and y that are members of fractal I, if x and y are not equal, that happens if x and y are not equal, then the intersection of x and y is null, or is a null set. For an index family AI, for which I are members of the capital I, the set of indices, the condition becomes I is not equal to j. If I is not equal to j, then AI intersection AJ is null. So this is a condition, or this is expression that these individual sets within the family of sets fractal I are disjoint. If, for example, fractal I is a composition of set A and B, we simply say that A and B are disjoint. That's how you would say it or express it. We'd like to bring into consideration the idea of partition and equivalence relations. A partition of a set A is a set, or is a disjoint family fractal I of sets whose union is A. So if you can pull out individual sets that are disjoint, then you've partitioned that set. For example, if you have a set of 1, 2, 3, 4, 5 individual sets of union sets, unary sets, or set of individual elements 1, 2, 3, 4, 5, 6, those are partitions of that set. The elements of this family of set fractal I are called fibers. In other words, if you've partitioned your set into these different disjoint sets, then those are fibers of the disjoint of the set you've partitioned. We also say that fractal I fibers A, in other words, the family that you've created, it fibers the original set, or fractal I is a fibering of the original set A. So that brings us to the end of this treatment. In the next section now we begin looking at the bigger animal and that is vector space or vector spaces, and that brings us closer to now beginning to look at the real deal of calculus, the real treatment of it, beginning with differentiation and then moving forward to integration. It was an absolute pleasure going through this with you. Until next time, bye bye.